going over the sigmoid activation function. It's going to be important when we start doing our neural net. I'm going to show you how to create a sigmoid activation function gate with the gates that we talked about in the previous tutorial. Hope you enjoy the video.
Alright, for this tutorial we'll be going over the sigmoid activation function as well as potentially an introduction to neural networks. So, the sigmoid activation function is a function that I've written the formula out here, 1 divided by 1 plus e to the negative a. Right? And this gate right here, this ginormous gate that you see that's outlined in this dotted line, is the sigmoid activation function, and it's defined by smaller gates on the inside. So there's a negation gate, so that's negative a. There's an exponentiation gate, that's e to the negative a. There's an addition gate, so that's 1 plus e to the negative a. And then there's a division gate, so that's 1 over 1 plus e to the negative a. So 1 over 1 plus e to the negative a is the sigmoid activation function. You can see that we can create very complicated functions from just using this technique. Why is this useful at all? Well, we'll be explaining that later on. For now, we're going to go over the sigmoid activation function. What it does is it takes your inputs, the x-axis right here, and then it squashes them between 0 and 1. So very negative values go to 0, very positive values go to 1. Let's take a look at the backpropagation of this function. Backpropagation just means you're going to take your inputs and you're going to be like, okay, I'm just going to calculate what I calculated on slide 2 of the previous video. I'm going to take dp, it was dc in that video, and I'm going to push it through this derivative, and I'm going to say dp over b, right? dp over b. Where did I get the b? Well, you can see it's dc over b when it's dc, so it's dp over b here. How did I then why wasn't it dp over b here? Well, it is dp over b here, you just can't see it. The reason is what is b? Well, b is 1 plus e to the negative a. How did I get that? Well, this line right here is a, this line right here is b, right? So b is equal to, exponent of negative a plus 1. Exponent of negative a plus 1. How is that? Well, it's because this entire section right here is b, right? So here, the value here is exponent of negative a plus 1. And so that is dp over b essentially. Well, what is a? A is 1, right? Because a is 1 over b, which is equal to 1 plus e to the negative a. And then I go over here and confuse you even more because I say, but since it's a constant, it's actually 0. Why did I say that? Well, you see how it's 1 over 1 plus e to the negative a? 1 over 1 plus e to the negative a. 1 is not a variable. You cannot keep that derivative right there because it's a constant. And so therefore the derivative here is 0, which means that we can just cut that out of the entire equation. It's great because we don't actually need an arbitrary input. It's just 0. It just ends there. Same thing for this addition here. What did I do? Well, I essentially say dc is equal to dc here and then dc here, right? Well, what is dc for this addition block? Where am I getting the dc from, right? What am I saying here? Well, dc is equal to dc and dc for the derivative gate, for the plus, right? That's where I'm getting the dc from. Well, how do I define dc, right? dc is the derivative of this division block right here at that particular location. Well, what's the derivative of that particular location? Well, you can see it's negative a times dc over b times b. Well, we've already defined b as 1 plus e to the negative a. What is a? We've already defined a as well. It's 1, right? 1 over 1 plus e to the negative a. So that's essentially our output right there. And you can see that that's the same sort of format that this derivative follows. A is 1, b is here, and that's our division block. dc, 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 dc. Take a look at slide 2, and that should make sense for this addition block. And we're going to send this back to the exponentiation block, and we're going to say, all right, well, what does the exponentiation block do? It multiplies everything by e to the negative a, right? And so e to the negative a here, and this is right here, right? It multiplies it by e to the, actually just e to the a, sorry. Remember, e to the a. I got that wrong. It multiplies by e to the a, because that's the derivative of e to the x is e to the x. So it's e to the a. E to the a here multiplied by whatever this value of a is here. Well, a is essentially negative a, right? Because it's a here, negate it, and this is the input to the exponentiation. That's where we get the e to the negative a because it negates it here. And so we have to take a look at the right-hand side, chop it off here, take a look at the right-hand side, and that's going to be our input for the exponentiation block. And that's essentially what we have here, e to the negative a, right? And this negation block just takes that, and then we can say negates that value dc. So slowly go through it and take a look, and you will end up with this. And then you'll figure out that this is actually the derivative of this. If you actually know how to take the derivative. It's kind of a beautiful method that allows you to take the derivative of very complicated functions. And so that's going over the sigmoid activation function. And for now, we're actually going to just call this SIG or SIGMOID. We're just going to put all of this into a block, and we're just going to call it that, because it's just going to be easier when we look forward. In the next video, we're going to take a look at our first neural network. It's not going to be exactly a neural network with a hidden layer just yet, because that complicates problems, but it will be a problem where we will start writing some code either in the next tutorial or the tutorial after that. So you should start getting a better understanding of how these neural networks work.